Halt! Who goes there? I'm Ray Myers. Welcome to Craft vs. Cruft. And it's been a little while. Thanks for bearing with me. And we've been active getting the Empathy in Tech podcast started. We've got quite a few episodes. The last one's on technoethics. The next one will actually be an interview with J.B. Rainsberger, and had just a great time with that. But today I'd like to talk about program proofs, better known as formal verification, which is one branch of formal methods that also includes modeling and specification and type theory. Now, I believe program proofs are increasingly practical to start to think about as a complement to other ways we have of getting assurance in software engineering, like tests, like types, like plain old thinking about it. Now, when you start to explore this and bring it up, you run into this common misconception, which is that program proofs are simply impossible. Many people believe, and I used to believe, that the halting problem means that we can't prove what programs are going to do. The halting problem is one of the earliest results in computer science. It was first proven by Alonzo Church, who was the inventor of lambda calculus and was Turing's thesis advisor. When I was in school, the halting problem was talked about as kind of the prototypical example of a non-computable problem. A problem that is possible to define precisely, but that you could never make a program to solve it, and we've proven that you can't. So, what is that problem? It is the problem of determining whether another program will terminate. So again, that's no program can decide whether another arbitrary program terminates. Now, that word arbitrary is very important here. We're going to come back to that. You'll also hear this said as halting is undecidable. Being decidable is a little different than whether something is provable or not, because decidable means it must be determined by a general procedure. Proving an arbitrary mathematical theorem, that's not decidable, but it often is possible, right? We do it all the time. We just don't have a single program we could run that would always tell us if something had a proof or not, and we probably will never have that program. Something else that's cool about the halting problem is even though it is this really important result that has all these implications, the proof of it is very simple, charmingly simple. It was even put in a short poem by Geoffrey Pullum. That poem originally began,
"No program can say what another will do. Now I won't just assert that, I'll prove it to you. I will prove that although you may work till you drop, you cannot predict whether a program will stop."
No program can say what another will do. Already a bug in the first line. Do you see it? That's the misconception we're talking about. The corrected version, though a little bit clunkier, is no general procedure for bug checks will do. That's because the halting problem is a statement about our ability to check arbitrary code with a procedure. We still have the option of writing and checking code that is not arbitrary. We can do that, and we should do that. Not only can you write non-arbitrary code, but you can also write code that has a proof accompanying it. Now, although many software engineers have had the misconception that the halting problem rendered program proofs impossible, early computer scientists understood quite well the distinction that we're making here. And one of the first program proofs was actually published by Turing himself in 1949. Turing didn't say, well, my thesis advisor proved we can't prove anything about programs, so I'm giving... No, immediately we started proving things about programs. Now, knowing that it wasn't possible to do with a general procedure, computer science just carried on doing it another way. So this early program proof paper is called Checking a Large Routine, though the routine is not very large by today's standards. It is one of the earliest examples of a program proof. And you also know that people can prove things about programs if you've used type systems, right? You know, if you're in a statically checked language and you have a function called Fibonacci and it says it returns an integer, well, it's not going to screw around and return a string tomorrow, now is it? No matter what's in that code, the compiler has proven with some degree of rigor that if it returns a result at all, that it will be an integer result. That is a constraint that's being put on this Fibonacci function. Any number of things we might want to put in there, we can't because the type system won't accept them. But generally, we don't find this encumbers us. What we're doing here is we're writing non-arbitrary code, and we're in a system that is forcing us to write non-arbitrary code in that particular way. Now, depending on the language, we might not have to return at all. If we return, it must be an int, but perhaps we throw an exception. Perhaps we loop forever. Most type systems don't prevent us from doing so, but it is actually possible for type systems to determine just that. We can have the equivalent of a function signature that says not only does this return an int, but it does eventually return. It must terminate, and it must not throw anything. It may not always be desirable, but it is entirely possible to do that, to check that at compile time. Now, you do give up Turing completeness, if you're familiar with that concept, in the course of that. This is no longer an entirely arbitrary programming language, whatever comes after that. But again, we can still solve all manner of problems using non-arbitrary code, and I would argue that we should. You also intuitively know about program proofs if you've memorized facts about big O notation, time complexity of how program runtime grows as the input size grows. So people who have this misconception about what the halting problem implies, many of them also have memorized facts about the big O complexity of different algorithms and are probably aware on some level that that has been proven. Those properties, right? This isn't just a guess of what the runtime of bubble sort is. So really, you already know enough to think your way out of this misconception. Like, no reasonable person would say that we have no way of knowing for sure that bubble sort terminates. Now, the program proofs I've been talking about how we know things about big O notation and Turing's early program proofs, these are informal methods being applied. These are human-checked proofs. Whereas when we talk about formal verification, these are machine-checked proofs. So now we're bringing in another technology, which is automated theorem proving, and that was introduced in the mid-1950s. It's becoming increasingly powerful, increasingly used at the cutting edge of mathematics, including pretty extensively by Terrance, one of the world's leading mathematicians. So you combine the notion of doing program proofs with the notion of automated theorem proving, having machine-checked proofs. You combine those and you've got formal verification. A program-checked proof about another program. So what are some of the technologies that do this? Well, an interactive automated theorem prover, sometimes called a proof assistant, and Lean is my current favorite. I recently did a video on it. I'll probably do a lot more. COQ is another, and Isabelle. These are some popular proof assistants. And some other programming languages that have proof features in them include Dafny, ACL2, Idris, and Agda. And these are at different points on, for instance, a spectrum of being more mathematically oriented and more versus more industry oriented, with Dafny being maybe the most industry friendly because it compiles to a number of other languages like Java and JavaScript. So we see that formal verification is possible, is very real. We can prove code in some sense to be bug-free, at least relative to its spec. But why are you just now hearing about this, right? Like, why is this so rarely used still? Well, it's true that it's not impossible, but it does have a reputation for being just extraordinarily difficult. And that's not entirely a myth. That's kind of true. It's hard. This stuff makes my head hurt. But it is getting easier. I mean, once upon a time, if you could verify even a program of a few dozen lines, I mean, congratulations. That is a feat. Take the week off. Maybe publish a paper. So this kind of painstaking effort was only applied in industry to just the most critical of critical code. Like, it might be something controlling how planes land, or it might be a piece of cryptography. But these were very isolated use cases that justified the cost of doing this. The work they put in making that possible started to pay off and making it possible in more and more places, though. I don't think any single advance has changed that. It's taking many things, but it is changing. It is becoming more approachable. Some examples of those advances. We're becoming better at restricting a programming language for provability without trading as much usefulness. We've seen this, for example, in the proliferation of richer type systems. Null safety is becoming more mainstream. Memory safety is becoming more mainstream. We are also making more powerful and friendlier proof assistants. And we're also learning how to teach these concepts better that enable this. Concepts like dependent types, for instance. Various kinds of bridges, integrations have been created between provers and industrial languages. And we're developing architectural patterns that optimize the cost benefit, like a verified core or a proven reference implementation, like AWS used in Cedar, for instance. Now, it'd be interesting to imagine a world where all code had been formally verified in some sense, but what I've learned from beginning to learn and apply these techniques is that you can get an amazing amount of value from just a little bit of usage on some critical area or just on your design. So that's about enough from me for today. I hope I've sparked your curiosity about this. I will, of course, link some resources and look forward to your questions in the comments. As Lao Tzu said in the Tao Te Ching, with patience, the most tangled cord may be undone. Thank you.